हेलो फ्रेंड्स, आज हम लोग एक नए टॉपिक के बारे में डिस्कस करेंगे which is topology, or you can say topological space. Now first you need to understand what is a topology. I hope everyone knows set theory because this is the basic you need to understand topology. So the definition is, let X be a set and tau be a collection of subsets of X. टाउ जो है वो X का कुछ सबसेट्स का कलेक्शन है. नाउ ये कलेक्शन ऑफ सेट्स जो है वो टोपोलॉजी कब बनता है? सो देयर आर थ्री कंडीशंस अंडर व्हिच X becomes tau becomes a topology. Then tau is a topology if number one empty set or whose X जो है set X and the empty set belongs to tau. First condition. Second condition, for any arbitrary collection u alpha lambda of members of tau. It means in this collection all the members, all the u alpha belongs to tau. Okay, so you pick any sub collection, you can say sub collection of tau, then union of the sub collection is a member of tau. And number 3 is for any two u1 u2 belongs to tau, any two member of tau. If you take any two member of tau, then intersection of these two members belongs to tau. Now if any collection of subsets of X satisfies these three conditions, then tau is said to be a topology. Okay, and consequently the pair X comma tau is called topological space, or you can say X is a topological space with respect to the topology tau. यहाँ पे एक बात है कि एक पर्टिकुलर सेट का एक ही टोपोलॉजी होगा वो कोई गारंटेड नहीं है, बहुत सारा टोपोलॉजी हो सकता है. ओके, तो उसमें से जो दो कॉमन टोपोलॉजी हैं वो कौन से हैं? टू कॉमन टोपोलॉजीज आर indiscrete topology. Indiscrete topology में क्या होता है? Pick any set X and take tau as phi and X. And this is a indiscrete topology. कैसे? Because there are only two members, दो ही member है, phi इसके अंदर है, X इसके अंदर है, so condition 1 is satisfied. Now the only possible collections are phi itself, X itself, or both. So if you take union of any of this, you will get the same thing. So if you take union of only phi, you will get phi, only X, you will get X. If you get the union of phi and X, then X. So in any way, arbitrary union of member of tau is a member of tau. And for intersection, there are only two members. So if you intersect phi and X, then you will get phi, which is again a member of tau. So this is a topology. This is indiscrete topology, and another is discrete topology. What is discrete topology? For any set X, the discrete topology tau is nothing but power set of X. So if you consider the power set of X, you know power set of X. Power set of X is the collection of all the subsets of X. So if you consider all the subsets of X, then that particular collection also becomes a topology because phi is there, X is there. If you take arbitrary union of any collection, it is again a subset of X, which by definition of power set belongs to X, belongs to the power set. and if you pick any two member from the part set of X, and if you intersect them, then again it will become a subset of X. Then by the definition of part set, it again belongs to a part set. So all the three conditions of topology are satisfied by this collection. So it becomes a topology, and this topology we call discrete topology. This is a indiscrete topology. There are properties for this topologies, unique properties are there. Okay, now next we can say what are the topologies other than these two. Now I will discuss only two topology because we need them in our future lectures. First is your usual topology on real number R. Okay, so what is that topology? If I define a collection of subset of R. Now what is the collection? All the subset G, subset of R, is contained in U such that for each X belongs to G, there exists epsilon greater than 0 such that the open interval X minus epsilon comma X plus epsilon is a subset of G. Ignore the background sound. So this is a collection. This collection forms a topology, but it will form a topology if you consider this union of all. Okay, you have to consider this empty set because empty set contains no point. So showing this condition is impossible. Okay, this condition means for each point in X, for every point X in G, there is an open interval which contained in G. So this particular condition you cannot show in phi. So as you cannot show it does not belongs to you, it means it belongs to you. So we disregard those arguments and just take the union first. Okay. If you don't take also, then also we can make some argument that you cannot show that phi is not there. So it means phi is there. So we ignore those comments and consider phi as the union in this collection. Okay. So this is usual topology, and another is cofinite topology. There are other topologies. This is for real numbers. Okay. And cofinite topology you can consider it on any set. You can form. So cofinite topology is tau co. All the G. So the set is X. Okay. All the G subset of X such that X difference G is finite. Means complement of the G is a finite set. If complement of any set is finite, then that particular set belongs to the collection. So this collection also forms a topology on a set, and this topology is called cofinite topology. I will give the proof of these two when we will discuss the topological spaces. Okay, in our different lecture, different topological spaces like cofinite topology, then right ray topology, left ray topology, then topology on circle. Now there is a concept called final quasar topology. Weak topology and strong topology. Okay. So what is final and what is quasar? Quasar means it contains big sets. Final means it contains small sets. So by final and quasar topology, we can compare the topology in a given set. So let X be a set. Okay. Now there is a two topology, tau 1 and tau 2. Now if tau 1 is a subset of tau 2, then tau 2 is final, then tau 1. Or in other words, tau 1 is quasar than tau 2. Okay. Now, why I am showing this? If there are two topologies on X. Suppose there are topologies on X. Suppose this is X. Suppose not two. Suppose there are three topologies, and in some way I can show either this or this, anyone. Okay. Then we can say that these two topologies are comparable. Okay, incomparable topologies you can choose final one sometimes coarser one, but they mostly resemble the same thing. But tau 3, if you cannot show this is if not subset of this, or tau this, or tau 2 not subset of tau 3, or tau 3 not subset of tau 2, then tau 2 is incomparable. So it means it depicts a different picture. These two depicts the similar picture, but suppose this is the case, then with tau 3 we get a finer image, good image of the geometry. With tau 1 we get a coarser image of the geometry, but they resemble almost the same thing. But for tau 2, as they are incomparable, then the geometry of tau 2 will be a different one. So this is the case. So this is called comparable topologies. Two topologies are comparable if one is a subset of other. Okay. And this is the first lecture. I am showing just the glimpse. Okay. Now come to our last topic of this lecture, that is base. Base for a topology, because if you know the base, you can create for every base it corresponds a unique topology. But for a given topology there could be many bases. But for a given base there is a unique topology. So independently we can define base. But for the general understanding, what is a base? If you have a topology, then if you have a collection, suppose if you have a topology, so suppose if you have a topology tau, and you have a subcollection C from tau, and the collection is chosen in such a way that if you pick any member from this one tau, then this member can be represented as the union of members of script C. Okay, if you pick any member from tau, then that particular member can be represented as the union of members of script C. If this is true for every member of tau, then we say C is a base for tau. Now this is a very crude definition. I usually follow the definition of James Munkier's, which is, I think, a better definition or an independent definition for base. For that you no need to find the topology. A collection could be a base for a unique topology or for a topology if few conditions are satisfied. Okay, if you have a collection, you can say this collection can form a topology if it satisfies few things. Okay, so let X be a set and script B be a collection of subsets of X, then script B is a base if number 1, for all X belongs to X, there exists B belongs to script B such that X belongs to B subset X. This is the first condition. Second condition, for any two B1, B2 belongs to script B, and any X belongs to B1 intersection B2, and for any X belongs to B1 intersection B2, then there exists B B3 belongs to script B such that X belongs to B3 subset of B1 intersection B. Now, if any collection satisfies these two conditions, then you can say this will form a base for some topology. What is the topology? We may not know. We have to take the arbitrary union of members of script B, then you can generate the topology. That is fine. We don't know the topology now, but it could be a base for some topology. So if you can find the base, you can generate the topology. So this is the independent definition. It will be you can find the definition in James Mockier's. This particular definition is equivalent to the definition that I have stated just before this one, that if any member of tau can be represented as arbitrary union of members of any member of a topology can be expressed as a union of members of suppose script B, then script B can be said, then script B is said to be a topology base for tau. So these two definitions are actually equivalent. You can prove either one. Considering suppose statement 1, you can prove statement 2. Considering statement 2, you can prove statement 1. So this is the definition of a base, and with this definition I am closing the lecture with a simple definition, because you are studying topology. It means you know matrix space. So in matrix space you have learned open sets. Now what is open sets in topological space? In general, I am saying, in general in the sense, not in general word doesn't exist in mathematics, but I am saying in common language, any member of tau is open. Okay, so pick any member, it is open. So then what could be the definition? If you don't know the topology, suppose you don't know the topology, you only know the base, or you know a base of a base for a topology, but you don't know the actual topology, or the topology is so big that you cannot even express. So how can you find an open set in X? So for that, let X be a topological space, or you can say X is a set also. X is a set. Okay, no need to say topological space. And script B is a base. You know X is a set. You know the script B is a base by definition of base that you can just provide it. So let U X be any subset. Okay. If U equal to empty set, then U belongs to tau, which is open. Because empty set is there, you know empty set is there, so there is no question of asking the things that whether it's open or not, because empty set is a member of tau. Now what if this is not empty, U is not empty, then for every X belongs to U, there exists at least one B belongs to script B. For every X belongs to U, okay, every member of U, there exists a member in base such that X belongs to B subset of U. If this is true for a set, for a particular set, then that particular set is open in X. Remember, we don't know the topology yet. We can generate the topology. If you by looking at B, so script B, if you can generate the topology, then each member of the topology are the open sets of X. If any member is outside the topology, then that member is not open. Okay, any member of the topology is open. But in case you don't know the topology, then how to find the open set? This is the thing. If any set of X is open, if for every member of U there exists at least one member capital B of belongs to script B, such that X belongs to B subset of X. Okay. So this is how you can find open set in topological space. So this is the end of this lecture. In the next lecture, I will provide some examples, because today I haven't provided any examples, only introduced two things, that is usual topology and cofinite topology, and in the next lecture we'll go further. Okay.